And improper integrals gave us a way to find areas under curves if you were to allow the limit of integration to go all the way to infinity. So we saw that sometimes that will give us an actual answer. If that area gave us an answer, we said that that area converged, okay? If it didn't give us an area, then it diverged. So sometimes we found out that in trying to apply that improper integral, sometimes it converged, sometimes it diverged. Well, we're going to be now looking at something referred to as sequences and series. Now, we learned about these in some detail, some minimal detail in college algebra. When we were talking about arithmetic sequences, geometric sequences, you might remember there were a couple of formulas for being able to add up a certain number of terms. Well, we're going to be looking at this from the perspective of calculus at this point and looking at them in terms of limits. Okay, so we are going to start off by just defining a sequence. These are the lecture notes. I'm just going to go over a couple of things from here briefly, and then we'll look at a couple of examples. But most important thing to recognize here is that sequences are going to be represented by this symbol here, a sub n. Okay. And a sub n is only going to be defined for integer values, whole numbered integer values, or rather natural numbers. So I can't plug in, for instance, to some sequence if I have a sequence formula, okay? It's kind of like a function, except I can only plug in whole numbers. I can only plug in 1 and 2 and 3 and 4 and 5. It makes no sense for me to maybe replace n with 2.37. Okay, so the way that these are different than functions is that functions are often defined for whole spans of numbers, or often defined for all real numbers, while sequences are only defined for the positive integers. Okay, and so a sequence is nothing more than just a set of numbers that follow a particular pattern. So 3/5, and then -4/25, and then 5/125, and -6/625, and then 7/300125. These are numbers that are in a sequence that are forming some particular pattern. We may not know right away what that pattern is, but I'm going to go over how we can kind of imply what it is based off of some little tools here. So the first thing I would look at is, well, I know that every one of these terms is a fraction. It looks like the numerator terms change in a particular way, and the denominator terms change in a particular way. So I'm just going to start with each one of them separately. Now, the most important thing to start off by doing is to recognize that A1 or A sub 1 is the first term. Second term is called A2. The third term is A3, and so on. And so what that means is if I plug in 1, I should get an answer of 3/5. If I plug in 2, I should get an answer of -4/5. If I plug in 3, I should get an answer of 5/125. So I'm going to just start with the denominator and recognize that in order to get 5, 25, 125, 625, those all look like powers of 5. So that's why I'm going to start by just recognizing that the denominator will be 5 to the power of n. 5 to the first is 5. 5 to the second power is 25. 5 to the third power is 125. 5 to the fourth power is 625. So I know that the denominator is handled just by 5 to the n. Now I'm going to take a look just at the change here. So I'm going to forget about the sign for a minute because I don't know what the deal is with that changing back and forth from negative to positive. But I can see that it changes from 3 to 4 to 5 to 6 to 7. So it looks like I plug in 1 to get 3. You plug in 2 to get 4. You plug in 3 to get 5. So it looks like the value here is always 2 more than what n is, which is why I know that the numerator in this case would have an n plus 2, which would be right here. So we've handled the n plus 2 part, we've handled the 5n part. Now we got to figure out how can we change from negative to positive. And there's a very particular way to cause things to change from negative to positive. So there's a very particular way to cause terms to change from positive to negative. And the way that that happens is that anytime you see the terms alternate from positive to negative, you just take -1 and raise it to a power. So let's just think about what that does. If I plug in, if I just look at a sub n for this sequence here, -1 to the first power starts with -1. -1 to the second power changes to a +1. Then -1 to the third changes to -1. Then -1 to the fourth changes back to +1. So you can see that this situation is what happens when it changes from negative to when a sequence changes from negative to positive. But that's not really what happened up here, because notice that it started with a positive number, or I'm sorry, then it changed to a negative, then it changed to a positive. So the only thing we have to do to account for that is here, by adding 1 to the exponent, all that does is it causes you to plug in 1, but for this to now be a power of an even amount, which now means that I plug in 1, but I'm really getting a positive number because -1 squared is positive. Okay, so you either, if it ever changes from positive to negative, that means that you're either going to have -1 to the n or -1 to the n plus 1. Okay, so that just gives you a brief little description of what sequences are, and that sequences are just going to be functions of n. So we're just going to take a look at this sequence down here and write out the first few terms. So a sub n equals n over n plus 1. If I were to just write out the first few terms of this, then A1 would just mean plug in 1 to the sequence, A2 would mean plug in 2 for n, A3 means plug in 3 for n, A4 means plug in 4 for n. So you can see that the numerator here is just n, which means that the numerator is the same as the subscript. The denominator is going to be 1 more than the numerator. So that's why you can see that the numbers tend to go from 1/2 to 2/3 to 3/4 to 4/5 and so on. Now, if I were to continue this, then eventually I would get a term of, say, 999 over 1,000, or 9,999,999 over 1 billion, right? You can see that those numbers tend to get closer and closer and closer to 1. And you can see that graphically by taking a look at this number line right here. Okay, if you take a look at this number line, I can see that the first term is halfway to 1. Second term got a little closer. Third term got closer. Fourth term got closer. But you can see the gap in between these numbers is getting smaller and smaller and smaller, to where A100 is still going to be really close to 1, but still smaller. So what we say is that this sequence converges to 1. We can even see this on a 2-dimensional graph. We can see this on a 2-dimensional graph here by recognizing that if you were to plot these values as real numbers on this number line, or on this Cartesian coordinate plane, just like we would with functions, we could label this axis down here as the x, we could label this as the x-axis. If that was the x-axis, though, then that would imply that I'm able to plug in virtually any number I want. So that means I should be able to plug in 4.5 and get some particular value, and plug in pi here and get some particular value, right, and so on. But this is not a function. This is a sequence, which means that I'm only able to plug in whole numbers, positive integers, which is why the graph of this sequence is nothing more than just a collection of a bunch of dots. What you definitely don't do is connect them. Do not connect points in a sequence. the sequence graph is just a collection of dots. And what we should notice is that when I plugged in 1, I got 1/2. When I plugged in 2, I got 2/3. When I plugged in 3, I got 3/4. And so you could see that this graph tends to get closer and closer and closer to some fixed value. And that's why we say that when we take the limit as n approaches infinity of a sub n, this is nothing more than 1. Cool. So that's why we say that a sub n converges. Okay, so a sub n converges to the limit L. So that's basically it. That's really all a sequence is. So a sequence is nothing more than just a formula that that tells you how each of the terms in the sequence are related to each other. And what our job is to determine whether or not this sequence ends up going off to infinity or whether it ends up staying around, approaching some particular number. Okay? All right. I would like to just go back up to this, this sequence right up here real quick. What about this? Does this sequence converge or diverge? I'm talking about this one right here. What do you think about this one? Does this sequence converge or does it diverge, do you think?
Diverge.
Why do you think it diverges?
It never approaches 0.
It never approaches 0. That's a good thought, but neither did this one down here. This one didn't approach 0, but it still converged. It converged to 1. So we don't say that it needs to go get closer to 0. We're just saying that in this case right here, this one happened to get closer to 1. Any number is fine. Okay, so it doesn't need to get closer to 0.
And the one that you just displayed, Professor Yegi, where you had like -1, 1, -1, 1. It's jumping to different parts of the graph, whereas a of n that we defined that was like 1/2, 2/3, 3/4. It's consistently has a trend of heading towards a particular number.
That's the key. Thank you, Abby, is that this right here has a trend of approaching a fixed number of 1. It's never going to get to 1, but it's going to converge to 1 because all of these numbers are getting closer and closer to that number. As opposed to this one up here, though, is that once you think that you're getting close to -1, you all of a sudden jump back to 1 again. And now you're like, oh, maybe it's converging to 1 then. So then you're like, oh, nope, sorry, it converged to, oh, wait, hold on, it jumped back to -1, and then it jumped to 1 again. So it's not really converging to any particular value, right? It's oscillating back and forth. And therefore, this sequence right here diverges.
Does not exist.
No, the sequence exists. We just say the sequence diverges.
My
Well, it
bad.
would go to infinity, right?
It wouldn't even go to infinity. This is what I'm trying to show is that divergent doesn't mean just go to infinity. It means does not go to a number. So converges means that the terms in the sequence will eventually approach a number. Diverges means it does not approach a fixed number. So sometimes a sequence that ends up going off to infinity diverges, but in this case right here, this sequence also diverges because it doesn't approach a fixed value. Okay, so diverges doesn't always mean goes off to infinity. Okay. What about this one right up here? Would you say this one converges or diverges? Would you say? Would you guess?
I would guess diverges.
Okay. Would anybody argue converges?
Why not? Sure.
I mean,
Okay. All right. So argue.
Well, the thing is that infinity isn't a number, so I don't know how it would converge to infinity.
That's true. So if it went to infinity, then we would say it diverges. So it does not converge if it goes to infinity. So you're saying that this one right here goes to infinity? That each of the numbers in the sequence eventually get closer and closer to infinity?
Yes.
Okay.
Oh wait, they look like
Looks
they're
like
getting
it's-
closer and closer to zero just from opposite sides of the x-axis.
Yeah, they do. Isn't 3/5, if I forget about the negatives and positives, isn't 3/5 bigger than 4/25? And isn't 4/25 bigger than 5/125? And 5/125 is bigger than 6/2625. And so it looks like, 7/3,125, that's pretty small. It looks like all of these numbers keep getting closer and closer to zero. They just keep bouncing back and forth from one side of the x-axis to the other. So if I were to take a look at this on a graph, this would just look like, when I plug in 1, I get 3/5. But when I plug in 2, I now get negative 4/25. And then I plug in 3, and I get positive 5/125. But look, they're bouncing back and forth, but as they're bouncing back and forth, it looks like they're getting closer and closer to the x-axis. And now they bounce over and I get to here. So you should be able to recognize that this one right here tends to go off to 0 as n approaches infinity. So we would say that this sequence up here converges to 0. Okay. Now there's different ways to actually compute these limits, but a lot of times the easiest way to do so is to actually make it a function and do so. So there's just one more thing that I wanted to talk about here. And that's L'Hopital's rule. One way to calculate limits, remember, was L'Hopital's rule. But remember, and the most important thing to recognize here is L'Hopital's rule does not apply to sequences. So I can't use L'Hopital's rule on this right here. Because in order to do so, ln of n has to be a differentiable function. N has to be a differentiable function. But they're not. Because remember, ln of n and n are just individual points. It's not a continuous graph. But what is kind of cool is that if you were to say that the limit of the function gives you a certain value, then it also means that the limit of the sequence will automatically give me the same value. And that's important to recognize here because it's basically, I don't think I wrote it out anywhere. Oh, there we did. So if the limit as x approaches infinity of the function goes to L, and f of n is equal to some sequence a sub n, then that tells me that the sequence will also go to L. And hopefully you recognize that that's obvious. If the red curve is f of x, and the green dots form what a sub n is, well, if the red graph goes off to the limit, then obviously those green dots are going to be approaching the same place. So the beauty of being able to use L'Hopital's rule here is that if I were to change all of my n's to x's, I could just actually do L'Hopital's rule with x's. L'Hopital's rule shows me that the limit of the function goes to 0, which automatically implies that the sequence also goes to 0. Everybody cool with that? So if you want to use L'Hopital's rule, really all you're doing is changing the sequence into a function of x, applying L'Hopital's rule, and then inferring that the sequence will also converge to that value.